Hello friends and welcome to PyShine. In this video, we'll talk about particle swarm optimization, which is also called PSO. We will implement the interactive PSO, in which the target can be changed. In Python, we will make two matplotlib figures, one for changing the target and another for observing how particles reach the target. The particles find target in their search boundary. Imagine an XY plane with some boundaries. A square, here, shows the area for the insects to search a target. Consider, the insects are at different locations. While moving randomly, one of them has found some food at the green location. This green location is the so far best, and this insect will inform others about this location. However, this is still not the optimal or biggest target, so how they will reach to that target? Imagine a swarm of living particles over an area where they can smell a hidden source of food. The one who is closest to the food makes the loudest sound, and the other particles move around in its direction. If any of the other moving particle comes closer to the target than the first one, it will make a louder sound, and the others will move toward it. This mechanism continues until one of them happens upon the food. PSO is originally attributed to Kennedy, Eberhardt and Shih. It was first intended for simulating social behavior as a stylized representation of the movement of organisms in a bird flock or fish school. At first, we initialize the particles. Next, we calculate the fitness values for each particle using a fitness or cost function. The fitness is commonly the difference between target value and the current value. While searching, if the current fitness is better than the local best, then we assign the current fitness as the new local best. If during an iteration, the current fitness is not better than the local best, then we retain the previous local best. The global best is the one which is better in all local best values of the particles. After that, based on these values, we calculate the next velocity to set for each particle. Then, we update the velocity and position of the particle. Based on the updated information, if the target is achieved, which means if the error is reduced to the desired value, we can end the searching process. Otherwise, we will proceed to next cycle. Alright, let's move to the coding part. First, we will make a Python file named draggable.py. Let's import the essentials. In matplotlib, the patches class has a number of shapes, such as circle, ellipse, arrow, fancy box, polygon, rectangle and wedge. We make a figure of size 4 by 4 inches. The x and y limits are set to -500 to 500. It means that we can move the target in these limits around the axis of this figure. Let's make the class draggable target, which will be used for the point in x and y axis that can be dragged using mouse movement. This point has certain attributes such as pressed, background, and ID. Let's make the setters and getters of the ID. Now, we will make the event connector, which will tell us when the mouse button press event is triggered. We will call the self.onPress function upon this event. Similarly, on the mouse release event, we will call the self.onRelease function. During the motion of dragged mouse, we will call the onMotion function. Now, we will define these functions. On press event, we will lock the draggable target to itself, get the canvas and axis of the point and draw the canvas. Since we have the X and Y axis position of the target from the press event, here, we will use the difference between new axis value and pressed value to update the target position on the canvas. Now, we will output this position to a target.csv file. The print function will use the write mode so that new data can be overwritten on this position. On release, we will set the press and background to none. Also, now the point does not require animation. To disconnect all connection IDs, we can call this function. We can have a list of circle patches, but here, we require one circle at position 10, -10 and radius 20. If you want to put more draggable circles, simply add more patches to the circles list. Let's iterate this list and add a circle to the axis. Finally, we will show the legend of label and show the plot. Alright, let's run it to check if the target can be dragged as expected. As you can see, once we press the target and move it, the target.csv file is generated with X and Y position data. Next comes the main.py file. Let's import the essentials. Here, we will use the thread module to call the draggable.py file. The start drag function will execute this command line code to call the Python file. Here, if your name is set as Python 3, then please change it to Python 3 instead of Python. Here, we set the initial position to 5, and bounds are set larger than those in the draggable, so that we don't lose the particles during target movement. Let's set about 80 different RGB color values. These values can help us to color and differentiate different particles. Alright, let's define the particle class. Here, we initialize the position, velocity, best local position, best local error, and current error. The search boundary has only 2 dimensions, x and y-axis values. So we randomly initialize the velocity and position for each dimension. The update velocity function will set the best velocity, depending on the global best position of the particle. Here, we have the inertia weight and cognitive weights for the local and social aspects. The cognitive velocity will use random variable, R1, and the global velocity will use random variable, R2. So, the updated velocity will be the sum of these two. Let's make the update position function. The position is updated based on the velocity, and the particle is kept within the defined bounds. Now, we will make the evaluate fitness function. Based on the position of the particle from the target, the fitness function will give us the error value. If the error is less than the so far best error for the particle, the best position as well as the best error will be updated here. The fitness function will read the CSV file and give us the XY position of the target. Then, we can use the distance between target and the current position of the particle as the returned fitness value. The getXY function will read the CSV file and return the position. Based on the above functions and parameters, let's make the interactive PSO class. The number of dimensions is set as global so that it can be accessible to the particle class. We set the global best error as -1 and introduce a parameter called gamma that will decide the speed of convergence towards the target. Based on the number of the particles, we append them to this swarm list. Instead of setting a while loop for the maximum number of iterations, here, we will run the while loop forever to keep the environment interactive. For each particle, we will evaluate the fitness function. It will give the best error and the best position to each particle. Now, we obtain the global best position and the global best error, upon these conditions are met. Here, we update the title with information. At each alternate iteration, we will set the global values to keep the environment interactive for any change in the target position. We will keep on updating the position and velocity of each particle. The pose dictionary has now position of each particle. We will use it to plot the particles on the canvas of Matplotlib figure. Here, under the given limits, we plot each particle with a specific color. We will also plot the target as well. The update of canvas is set to 0.01 seconds. You can change it according to your specifications. After each update, the plot is cleared. After printing the values, let's call this class and set the particles to 32. You can also add the max iteration parameter here, let's say for example 2 particles and 50 iterations. Finally, let's run the code. We can see that now 2 figures are available, and we can use the left figure to set the target position. As we move the target, the particles try to minimize the cost, which is the distance between them and the target. Let's reduce the number of particles to 16. Now, we change it to 8. Let's do something more interesting. We set the particle to 1, which means no swarm, and just a single particle. Will it find the target or not? We observe that, without cooperation and due to lack of information, the particle failed to find the target and stuck to the boundary. That's all for today. If you have questions, suggestions, please comment, share, like and subscribe for upcoming interesting tutorials on PyShine. Have a nice day and see you again.